Hello students, welcome to the video. In this video, we will be reading the chapter Structure of Atom, Class 11, Unit 2. This video will be an audio book for your revision purpose. Structure of Atom. The rich diversity of chemical behavior of different elements can be traced to the differences in the internal structure of atoms of these elements. The existence of atoms has been proposed since the time of early Indian and Greek philosophers, who were of the view that atoms are the fundamental building blocks of matter. According to them, the continued subdivision of matter would ultimately yield atoms which would not be further divisible. The word atom has been derived from the Greek word atomio, which means uncuttable or non-divisible. These earlier ideas were mere speculations and there is no way to test them experimentally. These ideas remained dormant for a very long time and were reviewed again by the scientists in 19th century. The atomic theory of matter was first proposed on the firm scientific basis by John Dalton, a British school teacher in 1808. His theory, called Dalton's atomic theory, regarded the atom as the ultimate particle of matter. Dalton's atomic theory was able to explain the law of conservation of mass, law of constant composition, and law of multiple proportion very successfully. However, it failed to explain the results of many experiments. For example, it was known that the substances like glass or ebonite, when rubbed with silk or fur, gets electrically charged. In this unit, we start with the experimental observations made by scientists towards the end of 19th and beginning of 20th century. They established that atoms are made up of subatomic particles, that is electrons, protons and neutrons, a concept very different from that of Dalton. 2.1 Discovery of subatomic particles. An insight into the structure of atom was obtained from the experiments on electrical discharge through gases. Before we discuss these results, we need to keep it in mind a basic rule regarding the behavior of charged particles. Like charges repel each other and unlike charges attract each other. 2.1.1 Discovery of electron. In 1830, Michael Faraday showed that if electricity is passed through a solution of an electrolyte, chemical reactions occurred at the electrodes, which resulted in the liberation and deposition of matter at the electrodes. He formulated certain laws which you will study in class 12. This result suggested the particulate nature of electricity. In mid-1850s, many scientists, mainly Faraday, began to study electrical discharge in partially evacuated tubes, known as cathode ray discharge tubes. It is depicted in figure 2.1. A cathode ray tube is made up of glass containing two thin pieces of metal called electrodes sealed in it. The electrical discharge through the gases could be observed only at very low pressures and at very high voltages. The pressure of different gases could be adjusted by the evacuation of the glass tubes. When sufficiently high voltage is applied across the electrodes, current starts flowing through the stream of particles moving in the tube from negative electrode, that is cathode, to the positive electrode, that is anode. These were called cathode rays or cathode ray particles. The flow of current from cathode to anode was further checked by making a hole in the anode and coating the tube behind anode with phosphorescent material, zinc sulfide. When these rays, after passing through anode, strike the zinc sulfide coating, a bright spot is developed on the coating. The results of these experiments are summarized below. First one, the cathode rays starts from cathode and move towards anode. Second point, these rays themselves are not visible, but their behavior can be observed with the help of certain kind of materials, in bracket fluorescent or phosphorescent, which glow when hit by them. Television picture tubes are cathode ray tubes, and television pictures result due to fluorescence on television screen coated with certain fluorescent or phosphorescent materials. Third point, in the absence of electrical or magnetic field, these rays travel in straight lines. Fourth point, In the presence of electrical or magnetic field, the behavior of cathode rays are similar to that expected from negatively charged particles, suggesting that the cathode rays consist of negatively charged particles called electrons. Fifth point, the characteristics of cathode rays in bracket electrons do not depend upon the material of electrodes and nature of gas present in the cathode ray tube. Thus, we can conclude that electrons are basic constituent of all the atoms. 2.1.2 Charge to mass ratio of electron. In 1897, British physicist J.J. Thomson measured the ratio of electrical charge, that is E, to the mass of electron, represented as Me, by using cathode ray tube and applying the electrical and magnetic field perpendicular to each other as well as to the path of electron. When only electric field is applied, the electrons deviate from their path and hit the cathode ray tube at point A. That will be seen in figure 2.2. Similarly, when only magnetic field is applied, electron strikes the cathode ray tube at point C. By careful balancing the electrical and magnetic field strength, it is possible to bring back the electron to the path which is followed in the absence of electric or magnetic field, and they hit the screen at point B. Thomson argued that the amount of deviation of the particles from their path in the presence of electric or magnetic field depends upon, first point, the magnitude of the negative charge on the particle. Greater the magnitude of the charge on the particle, greater is the interaction with the electric or magnetic field, and thus greater is the deflection. Second point, the mass of particle, lighter the particle, greater is the deflection. Third point, the strength of the electric or magnetic field. The deflection of electrons from its original path increases with the increasing in voltage across the electrodes or the strength of the magnetic field. By carrying out accurate measurements on the amount of deflections observed by the electrons on the electric field strength or magnetic field strength, Thomson was able to determine the value of E by M as E by M will be equal to 1.758820 into 10 to the power 11 Coulomb per kg, where Me is the mass of electron in kg and E is the magnitude of charge on the electron in Coulomb. Since electrons are negatively charged, the charge on electrons is negative. 2.1.3 Charge on the electron. R.A. Millikan devised a method known as oil drop experiment to determine the charge on the electrons. He found the charge on the electron to be minus 1.6 into 10 to the power minus 19 Coulomb. The present accepted value of electrical charge is minus 1.602176 into 10 to the power minus 19 Coulomb. The mass of the electron was determined by combining these results with Thomson's value of E by M ratio. Mass of electron will be equal to E divided by E by M, that will be equal to 1.602176 into 10 to the power minus 19 Coulomb upon 1.758820 into 10 to the power 11 Coulomb per kg. That will be equal to 9.1094 into 10 to the power minus 31 kg. This is the mass of electron. 2.1.4 Discovery of protons and neutrons. Electrical discharge carried out in a modified cathode ray tube led to the discovery of canal rays carrying positively charged particles. The characteristics of these positively charged particles are listed below. First point, unlike cathode rays, mass of positively charged particles depends upon the nature of gas present in the cathode ray tube. These are simply the positively charged gaseous ions. Second point, the charge to mass ratio of particles depend on the gas from which these originate. Third point, some of the positively charged particles carry a multiple of the fundamental unit of electrical charge. Fourth point, the behavior of these particles in the magnetic or electrical field is opposite to that of observed 4 electrons or cathode rays. The smallest and lightest positive ion was obtained from hydrogen and was called proton. This positively charged particle was characterized in 1919, Later a need was felt for the presence of electrically neutral particle as one of the constituents of atom. These particles were discovered by Chadwick in 1932 by bombarding a thin sheet of beryllium by alpha particles. When electrically neutral particles having a mass slightly greater than that of protons were emitted, he named these particles as neutrons. The important properties of all these fundamental particles are given in Table 2.1. 2.2 Atomic Models. Observations obtained from the experiments mentioned in the previous sections have suggested that Dalton's indivisible atom is composed of subatomic particles carrying positive and negative charges. The major problem before the scientists after the discovery of subatomic particles were to account for the stability of atom. Second one, to compare the behavior of elements in terms of both physical and chemical properties. Third point, to explain the formation of different kinds of molecules by the combination of different atoms. And fourth point, to understand the origin and nature of the characteristics of electromagnetic radiation observed or emitted by the atoms. Millikan's oil drop method. In this method, oil droplets in the form of mist produced by the atomizer were allowed to enter through a tiny hole in the upper plate of electrical condenser. The downward motion of these droplets was viewed through the telescope equipped with a micrometer eyepiece. By measuring the rate of fall of these droplets, Millikan was able to measure the mass of oil droplets. The air inside the chamber was ionized by passing a beam of X-ray through it. The electrical charge on these oil droplets was acquired by collision with the gaseous ions. The fall of these charged oil droplets can be retarded, accelerated, or made stationary depending upon the charge on the droplets and the polarity and strength of the voltage applied to the plate. By careful measuring the effects of electrical field strength on the motion of oil droplets, Millikan concluded that the magnitude of electrical charge Q on the droplets is always an integral multiple of the electrical charge represented as small letter e, that is, Q will be equal to N into E, where N is integer, the values are 1, 2, 3 and so on. Different atomic models were proposed to explain the distribution of these charged particles in an atom. Although some of these models was not able to explain the stability of atoms, two of these models, one proposed by J.J. Thomson and the other proposed by Ernst Rutherford, are discussed below. 2.2.1 Thomson Model of Atom. J.J. Thomson in 1898 proposed that an atom possesses a spherical shape, radius approximately 10 to the power minus 10 meter, in which the positive charge is uniformly distributed. The electrons are embedded into it in such a manner as to give the most stable electrostatic arrangement. Many different names are given to this model, for example, plum pudding, raisin pudding, or watermelon. This model can be visualized as a pudding or watermelon of positive charge with plums or seeds in bracket electrons embedded into it. An important feature of this model is that the mass of the atom is assumed to be uniformly distributed over the atom. Although this model was able to explain the overall neutrality of the atom but was not consistent with the results of later experiments. Thomson was awarded Nobel Prize for Physics in 1906 for his theoretical and experimental investigations on the conduction of electricity by gases. 2.2.2 Rutherford's Nuclear Model of Atom. Rutherford and his student bombarded very thin gold foil with alpha particles. Rutherford's famous alpha scattering experiment is represented in figure 2.5. A stream of high-energy alpha particles from a radioactive source was directed at the thin foil of gold metal. The thin gold foil had a circular fluorescent zinc sulfide screen around it. Whenever alpha particles strike the screen, a tiny flash of light was produced at that point. The results of scattering experiment were quite unexpected. According to Thomson model of atom, the mass of each gold atom in the foil should have been spread evenly over the entire atom, and alpha particles had enough energy to pass directly through such a uniform distribution of mass. It was expected that the particles would slow down and change directions only by a small angles as they passed through the gold foil. It was observed that, first point, most of the alpha particles passed through the gold foil undeflected. Second point, a small fraction of the alpha particles was deflected by small angles. Third point, a very few alpha particles, that is 1 in 20,000, bounced back, that is, were deflected by nearly 180 degree. On the basis of the observations, Rutherford drew the following conclusions regarding the structure of atom. First point, most of the space in the atom is empty as most of the alpha particles passed through the foil undeflected. Second point, a few positively charged alpha particles were deflected. The deflection must be due to enormous positive force, showing that the positive charge of the atom is not spread throughout the atom as Thomson had pre-assumed. The positive charge has been concentrated in very small volume that repelled and deflected the positively charged alpha particles. Third point, calculations by Rutherford showed that the volume occupied by the nucleus is negligibly small as compared to the total volume of the atom. The radius of the atom is about 10 to the power minus 10 meter, while that of nucleus is 10 to the power minus 15 meter. One can appreciate this difference in size by realizing that if a cricket ball represents a nucleus, then the radius of atom would be 5 km. On the basis of above observations and conclusions, Rutherford proposed the nuclear model of atom. According to this model, first point, the positive charge and most of the mass of the atom was densely concentrated in extremely small region. This very small portion of the atom was called nucleus by Rutherford. Second point, the nucleus is surrounded by electrons that move around the nucleus with a very high speed in circular paths called orbits. Thus, Rutherford's model of atom resembles the solar system, in which the nucleus plays the role of sun and the electrons that of revolving planets. Third point, electrons and the nucleus are held together by electrostatic force of attraction. 2.2.3 Atomic number and mass number. The presence of positive charge on the nucleus is due to the protons in the nucleus. As established earlier, the charge on the proton is equal but opposite to that of electron. The number of protons present in the nucleus is equal to the atomic number. For example, the number of protons in the hydrogen nucleus is 1. In sodium atom, it is 11. Therefore, their atomic numbers are 1 and 11 respectively. In order to keep the electrical neutrality, the number of electrons in an atom is equal to the number of protons. For example, the number of electrons in hydrogen atom and sodium atom are 1 and 11 respectively. Atomic number is represented as capital letter Z will be equal to number of protons in the nucleus of an atom. That will be equal to number of electrons in a neutral atom. While the positive charge of the nucleus is due to protons, the mass of the nucleus is due to protons plus neutrons. As discussed earlier, protons and neutrons present in the nucleus are collectively known as nucleons. The total number of nucleons is termed as mass number, represented as capital letter A of the atom. Mass number will be equal to number of protons plus number of neutrons. 2.2.4 Isobars and isotopes. The composition of any atom can be represented by using the normal element symbol in bracket capital letter X with superscript on the left hand side as the atomic mass number represented as capital letter A and subscript represented as Z on the left hand side as the atomic number, that is X with the superscript capital letter A with the subscript capital letter Z. Isobar are the atoms with the same mass number but different atomic numbers. For example, carbon, which has atomic number 6, mass number 14, and nitrogen, which has atomic number 7 and mass number 14. On the other hand, atoms with identical atomic number but different atomic mass number are known as isotopes. In other words, it is evident that difference between the isotopes is due to the presence of different number of neutrons present in the nucleus. For example, considering of hydrogen atom, again 99.985% of hydrogen atoms, certainly only one proton. This isotope is called protium, represented as H with subscript 1 with superscript 1. Rest percentage of hydrogen atom consists of two other isotopes. The one containing one proton and one neutron is called deuterium, represented as capital letter D, and the other one possessing one proton and two neutrons is called tritium, represented as capital letter T. The latter isotope is found in trace amounts on Earth. Other examples of commonly occurring isotopes are carbon atoms containing 6, 7 and 8 neutrons besides 6 protons. Chlorine atoms containing 18 and 20 neutrons besides 17 protons. Lastly, an important point to mention regarding isotopes is that chemical properties of atom are controlled by the number of electrons, which are determined by the number of protons in the nucleus. Number of neutrons present in the nucleus have very little effect on the chemical properties of an element. Therefore, all isotopes of given element show same chemical behavior. 2.2.5 Drawbacks of Rutherford model. As you have learned above, Rutherford nuclear model of an atom is like a small-scale solar system with the nucleus playing the role of the massive sun and the electrons being similar to the lighter planets. When classical mechanics is applied to the solar system, it shows that the planet describes well-defined orbits around the sun. The gravitational force between the planets is given by the expression G m1 into m2 divided by r square, where m1 and m2 are the masses, r is the distance of separation of the masses, and g is the gravitational constant. The theory can also calculate precisely the planetary orbits, and these are agreement with the experimental measurements. The similarity between the solar system and nuclear model suggests that electrons should move around the nucleus in well-defined orbits. Further, the Coulomb force in bracket K Q1 Q2 divided by r square, where Q1 and Q2 are the charges, r is the distance of separation of the charges, and k is the proportionality constant between the electron and the nucleus is mathematically similar to the gravitational force. However, when a body is moving in an orbit, it undergoes acceleration even if it is moving with a constant speed in an orbit because of changing direction. So, an electron in the nuclear model describing planet-like orbits is under acceleration. According to the electromagnetic theory of Maxwell, charged particles, when accelerated, should emit electromagnetic radiation. This feature does not exist for planets since they are uncharged. Therefore, an electron in an orbit will emit radiation. The energy carried by radiation comes from electronic motion. The orbit will thus continue to shrink. Calculations show that it should take an electron only 10 to the power minus 8 seconds to spiral into the nucleus. But this does not happen. Thus, the Rutherford model cannot explain the stability of an atom. If the motion of an electron described on the basis of the classical mechanics and electromagnetic theory, you may ask that since the motion of the electrons in orbits is leading to the instability of the atom, then why not consider electrons as stationary? Around the nucleus, if the electrons were stationary, electrostatic attraction between the dense nucleus and the electrons would pull the electrons towards the nucleus to form miniature version of Thomson's model of atom. Another serious drawback of the Rutherford model is that it says nothing about distribution of electrons around the nucleus and the energies of these electrons. 2.3 Developments leading to the Bohr model of atom. Historically, results observed from the studies of interaction of radiations with matter have provided immense information regarding the structure of atom and molecules. Niels Bohr utilized these results to improve upon the model proposed by Rutherford. Two developments played a major role in the formulation of Bohr model of atom. These were, first one, dual character of electromagnetic radiation, which means that radiation possesses both wave-like and particle-like properties. And second one, experimental results regarding atomic spectra. First, we discuss about the dual nature of electromagnetic radiation. Experimental results regarding atomic spectra will be discussed in section 2.4. 2.3.1 Wave nature of electromagnetic radiation. In the mid-19th century, physicists actively studied absorption and emission of radiation by heated objects. These are called thermal radiations. They tried to find out of what the thermal radiation is made. It is now a well-known fact that thermal radiation consists of electromagnetic waves of various frequencies or wavelengths. It is based on the number of modern concepts which were unknown in the mid-19th century. First active study of thermal radiation laws occurred in 1850s, and the theory of electromagnetic waves and the emission of such waves by accelerating charged particles was developed in the early 1870s by James Clerk Maxwell, which was experimentally confirmed later by Heinrich Hertz. Here we learn some facts about electromagnetic radiations. James Maxwell was the first to give comprehensive explanation about the interaction between the charged bodies and the behavior of electrical and magnetic field on macroscopic level. He suggested that when electrically charged particles moves under acceleration, alternating electric and magnetic fields are produced and transmitted. These fields are transmitted in the form of wave called electromagnetic waves or electromagnetic radiation. Light is a form of radiation known from early days, and speculations about its nature dates back to remote ancient times. In earlier days, light was supposed to be made up of particles. It is only in the 19th century when wave nature of light was established. Maxwell was again the first to reveal that light waves are associated with oscillating electric and magnetic character. Although electromagnetic wave motion is complex in nature, we will consider here only a few simple properties. First one, the oscillating electric and magnetic fields produced by oscillating charged particles are perpendicular to each other, and both are perpendicular to the direction of propagation of the wave. Simplified picture of electromagnetic wave is shown in figure 2.6. Second point, unlike sound waves or waves produced in water, electromagnetic waves do not require medium and can move in vacuum. Third point, it is now well established that there are many types of electromagnetic radiations which differs from one another in wavelength or frequency. These constitute what is called electromagnetic spectrum. Different regions of spectrum are identified by different names. Some examples are radio frequency region around 10 to the power 6 Hz used for broadcasting, microwave region around 10 to the power 10 Hz used for radar, infrared region around 10 to the power 13 Hz used for heating, ultraviolet region around 10 to the power 16 Hz, a component of sun's radiation. The small portion of around 10 to the power 15 Hz is what is ordinarily called visible light. It is only this part which our eyes can see or detect. Special instruments are required to detect non-visible radiation. Fourth point, different kinds of units are used to represent electromagnetic radiation. These radiations are characterized by the properties, namely frequency and wavelength. The SI unit for frequency is Hertz after Heinrich Hertz. It is defined as the number of waves that pass a given point in 1 second. Wavelengths should have the units of length. As you know that the SI unit of length is meter, since electromagnetic radiation consists of different kinds of waves of much smaller wavelengths, smaller units are used. Figure 2.7 shows various types of electromagnetic radiations which differ from one another in wavelengths and frequencies. In vacuum, all types of electromagnetic radiation, regardless of wavelength, travel at the same speed, that is 3 into 10 to the power 8 meter per second. This is called speed of light and is given by the symbol c. The frequency nu, wavelength lambda and the velocity of light is c are related by the equation c is equal to nu lambda. The other commonly used quantity, especially in spectroscopy, is the wave number. It is represented as nu bar. It is defined as the number of wavelengths per unit length. Its unit is reciprocal of wavelength, that is meter inverse. However, commonly used unit is centimeter inverse. 2.3.2 Particle nature of electromagnetic radiation, Planck's quantum theory. Some of the experimental phenomena such as diffraction and interference can be explained by the wave nature of the electromagnetic radiation. However, following are some of the observations which could not be explained with the help of even the electromagnetic theory of 19th century physics, known as classical physics. First point, the nature of emission of radiation from hot bodies, also known as black body radiation. Second point, ejection of electrons from metal surface when radiation strikes it. It is also known as photoelectric effect. Third point, variation of heat capacity of solids as a function of temperature. Fourth point, line spectra of atoms with special reference to hydrogen. These phenomena indicate that the system can take energy only in discrete amounts. All possible energies cannot be taken up or radiated. It is noteworthy that the first concrete explanation for the phenomenon of blackbody radiation mentioned above was given by the Max Planck in 1900. Let us first try to understand this phenomenon, which is given below. Hot objects emit electromagnetic radiations over a wide range of wavelengths. At high temperatures, an appreciable proportion of radiation is in the visible region of the spectrum. As the temperature is raised, a higher proportion of short wavelengths, that is blue light, is generated. For example, when an iron rod is heated in a furnace, it is first turns to dull red and then progressively becomes more and more red as the temperature increases. As this is heated further, the radiation emitted becomes white and then becomes blue as the temperature becomes very high. This means that red radiation is most intense at the particular temperature and the blue radiation is more intense at another temperature. This means intensity of radiations of different wavelengths emitted by hot body depends upon its temperature. By late 1850s, it was known that objects made up of different material and kept at different temperatures emit different amounts of radiation. Also, when the surface of an object is irradiated with light, a part of radiant energy is generally reflected as such, a part is absorbed and a part of it is transmitted. The reason for incomplete absorption is that ordinary objects are as a rule imperfect absorption of radiation. An ideal body which emits and absorbs radiation of all frequencies uniformly is called a black body, and the radiation emitted by such body is called black body radiation. In practice, no such body exists. Carbon black approximates fairly closely to black body. A good physical approximation to a black body is a cavity with a tiny hole, which has no other opening. Any ray entering the hole will reflect it by the cavity walls and will be eventually absorbed by the walls. A black body is also a perfect radiator of radiant energy. Furthermore, a black body is in thermal equilibrium with its surroundings. It radiates same amount of energy per unit area as it absorbs from its surrounding in any given time. The amount of light emitted from a black body and its spectral distribution depends only on its temperature. At a given temperature, intensity of radiation emitted increases with the increase of wavelength, reaches a maximum value at the given wavelength, and then starts decreasing. With further increase of wavelength as shown in figure 2.8, also as the temperature increases, maxima of the curve shifts from short wavelength. Several attempts were made to predict the intensity of radiation as a function of wavelength, but the result of the above experiment could not be explained satisfactorily on the basis of wave theory of light. Max Planck arrived at the satisfactory relationship by making the assumption that absorption and emission of radiation arises from oscillator, that is, atoms in the wall of the black body. Their frequency of oscillation is changed by interaction with the oscillators of electromagnetic radiation. Planck assumed that radiation could be subdivided into discrete chunks of energy. He suggested that atoms and molecules could emit or absorb energy only in discrete quantities and not in continuous manner. He gave the name quantum to the smallest quantity of energy that can be emitted or absorbed in the form of electromagnetic radiation. The energy of a quantum of radiation is proportional to its frequency and is expressed by equation E is equal to h nu. The proportionality constant h is known as Planck's constant and has the value 6.626 into 10 to the power minus 34 joule second. With this theory, Planck was able to explain the distribution of intensity in the radiation from black body as a function of frequency or wavelength at different temperatures. Quantization has been compared to standing on staircase. A person can stand on any step of staircase, but it is not possible for him or her to stand in between two steps. The energy can take only one value from the following set, but cannot take any values between them. E is equal to 0, h nu, 2h nu, 3h nu, and so on. Photoelectric effect. In 1887, H. Hertz performed a very interesting experiment in which electrons were ejected when certain metals were exposed to beam of light as shown in figure 2.9. The phenomenon is called photoelectric effect. The results observed in these experiments were: first one, the electrons are ejected from the metal surface as soon as the beam of light strikes the surface. That is, there is no time lag between the striking of light beam and the ejection of electrons from the metal surface. Second one, the number of electrons ejected is proportional to the intensity or brightness of the light. Third one, for each metal there is a characteristic minimum frequency known as nu naught, also known as threshold frequency, below which photoelectric effect is not observed. At a frequency nu greater than nu naught, the ejected electrons come out with certain kinetic energy. The kinetic energy of these electrons increase with the increase of frequency of the light used. All the above results could not be explained on the basis of laws of classical physics. According to later, the energy content of the beam of light depends upon the brightness of the light. In other words, number of electrons ejected and the kinetic energy associated with them should depend upon the brightness of light. It has been observed that though the number of electrons ejected does not depend upon the brightness of light, that kinetic energy of the ejected electrons does not. For example, red light of any brightness may shine on piece of potassium metal for hours, but no photoelectrons are ejected. But as soon as even in very weak yellow light shines on the potassium metal, the photoelectric effect is observed. The threshold frequency nu naught for potassium metal is 5 into 10 to the power 14 Hz. Einstein in 1905 was able to explain the photoelectric effect by using Planck's quantum theory of electromagnetic radiation as a starting point. Shining a beam of light on the metal surface can therefore be viewed as shooting a beam of particles, the photons. When a photon of sufficient energy strikes on electrons in the atom of metal, it transfers its energy instantaneously to the electrons during the collision, and the electrons are ejected without any time lag or delay. Greater the energy possessed by the photon, greater is the transfer of energy to the electron, and greater is the kinetic energy of the ejected electrons. In other words, kinetic energy of the ejected electrons is proportional to the frequency of the electromagnetic radiation. Since the shrinking photon has energy equal to h nu and the minimum energy required to eject the electron is h nu naught, then the difference in energy, that is h nu minus h nu naught, is transferred as a kinetic energy of photoelectron. Following the conservation of energy principle, the kinetic energy of the ejected electron is given by the equation h nu will be equal to h nu naught plus half mv square, where me is the mass of the electron and v is the velocity associated with the ejected electron. Lastly, a more intense beam of light consists of large number of photons. Consequently, the number of electrons ejected is also larger, as compared to that in an experiment in which a beam of weaker intensity of light is employed. Dual behavior of electromagnetic radiation. The particle nature of light posed a dilemma for scientists. On other hand, it could explain the black body radiation and photoelectric effect satisfactorily, but on the other hand, it was not consistent with the known wave behavior of light, which could account for the phenomena of interference and diffraction. The only way to resolve the dilemma was to accept the idea that light possesses both particle and wave-like properties. That is, light has dual behavior. Depending on the experiment, we find that light behaves either as a wave or as a stream of particles. Whenever radiation interacts with matter, it displays particle-like properties in contrast to the wave-like properties, which it exhibits when it propagates. This concept was totally aligned to the way the scientists thought about matter and radiation, and it took them a long time to become convinced for its validity. It turns out, as you shall see later, that some microscopic particles like electrons also exhibit this wave-particle duality. 2.3.3 Evidence for the quantized electronic energy levels, atomic spectra. The speed of light depends upon the nature of the medium through which it passes. As a result, the beam of light is deviated or refracted from its original path as it passes from one medium to another. It is observed that when a ray of white light is passed through the prism, the wave with shorter wavelength bends more than the one with longer wavelength. Since ordinary white light consists of waves with all the wavelengths in the visible region, a ray of white light is spread out into series of colored bands called spectrum. The light of red color, which has longest wavelength, is deviated the least, while the violet light, which has shortest wavelength, is deviated the most. The spectrum of white light that we can see ranges from violet at 7.50 into 10 to the power 14 Hz to red at 4 into 10 to the power 14 Hz. Such a spectrum is called continuous spectrum. Continuous because violet merges into blue, blue into green, and so on. A similar spectrum is produced when a rainbow forms in the sky. Remember that visible light is just a small portion of the electromagnetic radiation. When electromagnetic radiation interacts with matter, atoms and molecules may absorb energy and reach to a higher energy state. With higher energy, these are in an unstable state. For returning to their normal energy state, the atoms and molecules emit radiations in various regions. of the electromagnetic spectrum. Emission and absorption spectra. The spectrum of radiation emitted by a substance that has absorbed energy is called an emission spectrum. Atoms, molecules, or ions that have absorbed radiation are said to be excited. To produce an emission spectrum, energy is supplied to a sample by heating it or irradiating it, and the wavelength or frequency of the radiation emitted as the sample gives up the absorption energy is recorded. An absorption spectrum is like the photographic negative of an emission spectrum. A continuum of radiation is passed through a sample which absorbs radiation of certain wavelengths. The missing wavelength, which corresponds to the radiation absorbed by the matter, leaves dark space in the bright continuous spectrum. The study of emission or absorption spectra is referred to as spectroscopy. The spectrum of visible light, as discussed above, was continuous as all wavelengths of the visible light are represented in the spectra. The emission spectra of atoms in the gas phase, on the other hand, do not show a continuous spread of wavelengths from red to violet. Rather, they emit light with only specific wavelengths with dark spaces between them. Such spectra are called line spectra or atomic spectra, because emitted radiation is identified by the appearance of bright lines in the spectra. Line emission spectra are of great interest in the study of electronic structure. Each element has a unique line emission spectrum. The characteristic lines in atomic spectra can be used in chemical analysis to identify unknown atoms in the same way as fingerprints are used to identify people. The exact matching of lines of the emission spectrum of atoms of a known element with the lines from an unknown sample quickly establishes the identity of the latter. German chemist Robert Bunsen was one of the first invigilators to use line spectra to identify elements. Elements like rubidium, cesium, thallium, indium, gallium, and scandium were discovered when their minerals were analyzed by spectroscopic methods. The element helium was discovered in the Sun by spectroscopic method. Line spectrum of hydrogen. When an electric discharge is passed through an gaseous hydrogen, the H2 molecule dissociate and the energetically excited hydrogen atoms produced emit electromagnetic radiation of discrete frequencies. The hydrogen spectrum consists of several series of lines named after their discoveries. Balmer showed in 1885 on the basis of experimental observations that spectral line are expressed in terms of wave number, then the visible line of the hydrogen spectrum obey the following formula. Nu bar will be equal to 109677 bracket open 1 by 2 square minus 1 by n square bracket close centimeter inverse, where n is an integer equal to or greater than 3. That is, n will be equal to 3, 4, 5, so on. The series of lines described by this formula are called Balmer series. The Balmer series of lines are the only lines in the hydrogen spectrum which appear in the visible region of the electromagnetic spectrum. The Swedish spectroscopist John Rydberg noted that all the series of lines in the hydrogen spectrum could be described by the following expression. Nu bar will be equal to 109677 into 1 by n1 square minus 1 by n2 square, unit is centimeter inverse, where n1 will be equal to 1, 2, 3 and so on. n2 will be equal to n1 plus 1, n1 plus 2 and so on. The value of 109677 centimeter inverse is called the Rydberg constant for hydrogen. The first 5 series of lines that corresponds to n1 equal to 1, 2, 3, 4, 5 are known as Lyman, Balmer, Paschen, Brackett and Pfund series, respectively. Table 2.3 shows this series of transition in the hydrogen spectrum. Figure 2.11, page 46, shows the Lyman, Balmer, Paschen series of transition for hydrogen atom. Of all the elements, hydrogen atom has the simplest line spectrum. Line spectrum becomes more and more complex for heavier atom. There are, however, certain features which are common in all line spectra. That is, line spectrum of element is unique, and second one, there is regularity in the line spectrum of each element. The question which arise are, what are the reasons for these similarities? Is it something to do with the electronic structure of atom? These are the questions need to be answered. We shall find later that the answer to these questions provide the key in understanding electronic structure of these elements. 2.4 Bohr's model for hydrogen atom. Niels Bohr in 1913 was the first to explain quantitatively the general features of the structure of hydrogen atom and its spectrum. He used Planck's concept for quantization of energy. Though the theory was not the modern quantum mechanics, it can still be used to rationalize many points in the atomic structure and spectra. Bohr model for hydrogen atom is based on the following postulates. First point, the electron in the hydrogen atom can move around the nucleus in the circular path of fixed radius and energy. These paths are called orbits, stationary states or allowed energy states. These orbits are arranged concentrically around the nucleus. Second point, the energy of an electron in orbit does not change with time. However, the electron will move from lower stationary state to higher stationary state when required amount of energy is absorbed by the electron, or energy is emitted when electrons move from higher stationary state to lower stationary state. The energy change does not take place in continuous manner. Third point, the frequency of radiation absorbed or emitted when transition occurs between two stationary states that differ in energy by delta E is given by nu equal to delta E by H, that will be equal to E2 minus E1 by H, where E1 and E2 are the energies of the lower and higher allowed energy states respectively. This expression is commonly known as Bohr's frequency rule. Fourth one, the angular momentum of an electron is quantized. In a given stationary state, it can be expressed as in equation mvr will be equal to nh by 2 pi, where n will be equal to 1, 2, 3 and so on. Where m is the mass of electron, v is the velocity and r is the radius of orbit in which electron is moving. Thus, an electron can move only in those orbits for which its angular momentum is integral multiple of h by 2 pi. That means angular momentum is quantized. Radiation is emitted or absorbed only when transition of electron takes place from one quantized value of angular momentum to another. Thus, an electron can move only in those orbits for which its angular momentum is integral multiple of h by 2 pi. That means angular momentum is quantized. Radiation is emitted or absorbed only when transition of electron takes place from one quantized value of angular momentum to another. Therefore, Maxwell's electromagnetic theory does not apply here. That is why only certain fixed orbits are allowed. The details regarding the derivation of energies of the stationary state used by Bohr are quite complicated and will be discussed in higher classes. However, according to Bohr's theory for hydrogen atom, first point, the stationary states for electrons are numbered n equal to 1, 2, 3 and so on. These integral numbers are known as principal quantum numbers. Point number 2. The radii of stationary states are expressed as Rn will be equal to n square A0, where A0 will be equal to 52.9 picometer. Thus, the radius of the first stationary state are called Bohr orbit is 52.9 picometer. Normally, the electron in the hydrogen atom is found in this orbit. As n increases, the value of R will increase. In other words, the electron will present away from the nucleus. Point number 3. The most important property associated with the electron is the energy of its stationary state. It is given by the expression En will be equal to minus RH 1 by n square, where n will be equal to 1, 2, 3 and so on, where RH is the Rydberg constant and its value is 2.18 into 10 to the power minus 18 joule. The energy of the lowest state, also called as ground state, is E1 will be equal to minus 2.18 into 10 to the power minus 18 1 by 1 square. That will be equal to minus 2.18 into 10 to the power minus 18 joule. The energy of the stationary state for n will be equal to 2 will be E2 will be equal to minus 2.18 into 10 to the power minus 18 joule into 1 by 2 square. That will be equal to minus 0.545 into 10 to the power minus 18 joule. Figure 2.11 depicts the energy of different stationary states or energy levels of hydrogen atom. This representation is called an energy level diagram. When the electron is free from the influence of nucleus, the energy is taken as 0. The electron in this situation is associated with the stationary state of principal quantum number n will be equal to infinity and is called as ionized hydrogen atom. When the electron is attracted by the nucleus and is present in orbit n, the energy is emitted and its energy is lowered. That is the reason for the presence of negative sign in the equation and depicts its stability relative to the reference state of zero energy and n will be equal to infinity. Number 4. Bohr's theory can also be applied to the ions containing only one electron, similar to that present in hydrogen atom. For example, helium plus, Li2 plus, beryllium 3 plus and so on. The energies of the stationary states associated with these kinds of ions are given by the expression En will be equal to minus 2.18 into 10 to the power minus 18 into Z square by n square joule. And radii by the expression Rn will be equal to 52.9 into n square divided by Z picometer, where Z is the atomic number and has the value 2, 3 for the helium and lithium atoms respectively. For the above equations, it is evident that the value of energy becomes more negative and that of radius becomes smaller with increase of Z. This means that electron will tightly bound to the nucleus. Fifth point, it is also possible to calculate the velocities of electrons moving in these orbits. Although the precise equation is not given here, quantitatively the magnitude of velocity of electrons increases with the increase of positive charge on the nucleus and decreases with increase of principal quantum number. 2.4.1 Explanation of line spectrum of hydrogen. Line spectrum observed in the hydrogen atom, as mentioned in section 2.3.3, can be explained quantitatively using Bohr's model. According to assumption 2, radiation is absorbed if the electron moves from the orbit of smaller principal quantum number to the orbits of higher principal quantum number, whereas the radiation is emitted if the electron moves from higher orbit to lower orbit. The energy gap between the two orbits is given by the equation delta E will be equal to E final minus E initial. Combining equation 2.13 and 2.16, we will get delta E will be equal to minus RH by NF square minus of RH by Ni square, where Ni and NF stands for initial orbit and final orbits. Delta E will be equal to RH into 1 by Ni square minus 1 by NF square. That will be equal to 2.18 into 10 to the power minus 18 joule into 1 by Ni square minus 1 by NF square. The frequency nu associated with the absorption and emission of the photon can be evaluated by using equation nu will be equal to delta E by H, that will be equal to RH by H into 1 by Ni square minus 1 by NF square. That will be equal to 3.29 into 10 to the power 15 into 1 by Ni square minus 1 by NF square in terms of Hertz. And in terms of wave number, we can write nu bar will be equal to nu by c. That will be equal to RH by HC into 1 by Ni square minus 1 by Nf square. That will come out to be 1.09677 into 10 to the power 7 into 1 by Ni square minus 1 by Nf square in terms of per meter or meter power minus 1. From Nf is greater than Ni and the terms in the parentheses is positive and the energy is absorbed. On the other hand, in case of emission spectrum, Ni is greater than Nf, delta E is negative and energy is released. The expression 2.17 is similar to that used by Rydberg, derived empirically using the experimental data available at that time. Further, each spectral line, whether in absorption or emission spectrum, can be associated to the particular transition in hydrogen atom. In case of large number of hydrogen atoms, different possible transitions can be observed and thus leading to the large number of spectral lines. The brightness or intensity of spectral lines depends upon the number of photons of same wavelength or frequency absorbed or emitted. 2.4.2 Limitations of Bohr's model. Bohr's model of hydrogen atom was no doubt an improvement over Rutherford's nuclear model, as it could account for the stability and line spectrum of hydrogen atom and hydrogen-like ions. For example, helium plus, Li2 plus, beryllium 3 plus and so on. However, Bohr's model was too simple to account for the following points. First point, it fails to account for the finer details of the hydrogen atom spectral observed by using sophisticated spectroscopic techniques. This model is also unable to explain the spectrum of atoms other than hydrogen. For example, helium atom which possesses only 2 electrons. Further, Bohr's model was unable to explain the splitting of spectral lines in the presence of magnetic field, also known as Zeeman effect, or an electric field known as Stark effect. Second point, it could not explain the stability of atoms to form molecules by chemical bonds. In other words, taking into account the points mentioned above, one needs a better theory which can explain the salient features of the structures of complex atoms. 2.5 Towards quantum mechanical model of the atom. In view of the shortcoming of the Bohr's model, attempts were made to develop more suitable and general model for atoms. Two important developments which contributed significantly in the formulation of such model were: first one, dual behavior of matter; second one, Heisenberg uncertainty principle. 2.5.1 Dual behavior of matter. The French physicist de Broglie in 1924 proposed that matter, like radiation, should also exhibit dual behavior, that is, both particle and wave-like properties. This means that just as photon has momentum as well as wavelength, electron should also have momentum as well as wavelength. De Broglie, from this analogy, gave the following relation between wavelength and momentum of the material particle. Lambda will be equal to h by mv, that will be equal to h by p, where m is the mass of the particle, v is its velocity and p is the momentum. De Broglie's prediction was confirmed experimentally when it was found that an electron beam undergoes diffraction, a phenomenon characteristic of waves. This fact has been put to use in making an electron microscope, which is based on the wave-like behavior of electrons, just as an ordinary microscope utilizes the wave nature of light. An electron microscope is a powerful tool in modern scientific research because it achieves a magnification of about 15 million times. It needs to be noted that, according to de Broglie, every object in motion has a wave character. The wavelength associated with ordinary objects are so short that their wavelength properties cannot be detected. The wavelength associated with electrons and other subatomic particles can, however, be detected experimentally. Results obtained from the following problems prove these points quantitatively. 2.5.2 Heisenberg Uncertainty Principle. Werner Heisenberg, a German physicist, in 1927 stated uncertainty principle, which is the consequence of dual behavior of matter and radiation. It states that it is impossible to determine simultaneously the exact position and exact momentum of an electron. Mathematically, it can be given as in equation 2.23. Delta x into delta p will be greater than or equal to h by 4 pi, or delta x into delta m into v will be greater than or equal to h by 4 pi, or delta x into delta v will be greater than or equal to h by 4 pi m, where delta x is the uncertainty in position and delta px is the uncertainty in momentum of the particles. If the position of the electron is known with high degree of accuracy, then the velocity of the electron will be uncertain. On the other hand, if the velocity of the electron is known precisely, then the position of the electron will be uncertain. Thus, if we carry out some physical measurements on the electron's position or velocity, the outcome will always depict as fuzzy or blur picture. The uncertainty principle can be best understood with the help of an example. Suppose you are asked to measure the thickness of sheet of paper with an unmarked meter stick. Obviously, the result obtained would be extremely inaccurate and meaningless. In order to obtain any accuracy, you should use an instrument graduated in units smaller than the thickness of sheet of the paper. Analogously, in order to determine the position of an electron, we must use a meter stick calibrated in units of smaller than the dimension of the electron. To observe an electron, we can illuminate it with light or electromagnetic radiation. The light used must have the wavelength smaller than the dimension of an electron. The high momentum photons of such light would change the energy of the electron by collision. In such process, we no doubt would be able to calculate the position of the electron, but we would know very little about the velocity of the electron after the collision. Significance of uncertainty principle. One of the important implications of the Heisenberg uncertainty principle is that it rules out existence of definite paths or trajectories of electrons and other similar particles. The trajectory of an electron is determined by its location and velocity at various moments. If we know where a body is at particular instant, and if we also know its velocity and the forces acting on it at that instant, we can tell where the body would be sometime later. We therefore conclude that the position of an object and its velocity fix its trajectory. Since for a subatomic object such as an electron, it is not possible simultaneously to determine the position and velocity at a given instant or to an arbitrary degree of precision, it is not possible to talk of the trajectory of an electron. The effect of Heisenberg uncertainty principle is significant only for motion of microscopic objects and is negligible for that of macroscopic objects. This can be seen from the following example. If uncertainty principle is applied to an object of mass, say about milligram in bracket 10 to the power minus 6 kg, then delta V into delta X, that will be equal to h by 4 pi m, that will be equal to Planck's constant 6.626 into 10 to the power minus 34 joule second upon 4 into 3.1416 into 10 to the power minus 6 kg. That will be nearly equal to 10 to the power minus 28 per meter square per second. The value of delta V into delta X obtained is extremely small and is insignificant. Therefore, one may say that in dealing with milligram-sized or heavier objects, the associated uncertainties are hardly of any real consequence. In the case of microscopic objects, Like an electron, on the other hand, delta V into delta X obtained is much larger, and such uncertainties are of real consequence. For example, for an electron whose mass is 9.11 into 10 to the power minus 31 kg, according to Heisenberg uncertainty principle, delta V into delta X, that will be equal to h by 4 pi m, that will be equal to 6.626 into 10 to the power minus 34 joule second upon 4 into 3.1416 into 9.11 into 10 to the power minus 31 kg. That will be equal to 10 to the power minus 4 per meter square per second. It is therefore means that if one tries to find out the exact location of an electron, say to an uncertainty of only 10 to the power minus 8 meter, then the uncertainty in velocity, that is delta V, would be 10 to the power minus 4 meter square per second upon 10 to the power minus 8 meter. That will be nearly equal to 10 to the power 4 meter per second, which is so large that the classical picture of the electron moving in Bohr's orbits cannot hold good. It is therefore means that the precise statement of the position and the momentum of electrons have to be replaced by the statement of probability that the electron has at the given position and momentum. This is what happens in the quantum mechanical model of the atom. Reasons for the failure of Bohr model. One can now understand the reasons for the failure of Bohr model. In Bohr model, an electron is regarded as a charged particle moving in well-defined circular orbits about the nucleus. The wave character of the electron is not considered in Bohr model. Further, an orbit is a clearly defined path, and this path can completely be defined only if both the position and the velocity of the electron are known exactly at the same time. This is not possible according to the Heisenberg uncertainty principle. Bohr model of hydrogen atom therefore not only ignores the dual behavior of matter but also contradicts Heisenberg uncertainty principle. In spite of these inherent weaknesses in the Bohr model, there was no point in extending Bohr model to other atoms. In fact, an insight into the structure of atom was needed which could account for wave-particle duality of matter and be consistent with Heisenberg uncertainty principle. This came with the advent of quantum mechanics. 2.6 Quantum mechanical model of atom. Classical mechanics based on Newton's law of motion successfully describes the motion of all macroscopic objects such as falling stone, orbiting planets, etc., which have essential particle-like behavior as shown in previous section. However, it fails when applies to microscopic objects like electron, atoms, molecules, etc. This is mainly because of the fact that classical mechanics ignores the concept of dual behavior of matter, especially for subatomic particles, and the uncertainty principle. The branch of science that takes into account this dual behavior of matter is called quantum mechanics. Quantum mechanics is a theoretical science that deals with the study of motions of the microscopic objects that have both observable wave-like and particle-like properties. It specifies the law of motion that these objects obey. When quantum mechanics is applied to a macroscopic objects in bracket for which wave-like properties are insignificant, the results are the same as those of the classical mechanics. Quantum mechanics was developed independently in 1926 by Werner Heisenberg and Erwin Schrödinger. Here, however, we shall be discussing the quantum mechanics which is based on the ideas of wave motion. The fundamental equation of quantum mechanics was developed by Schrödinger and it won him the Nobel Prize in Physics in 1933. This equation, which incorporates wave-particle duality of matter and proposed by de Broglie, is quite complex and knowledge of higher mathematics is needed to solve it. You will learn its solutions for different systems in higher classes. For a system such as an atom or a molecule whose energy does not change with time, the Schrodinger equation is written as H psi will be equal to E psi, where H cap is the mathematical operator called Hamiltonian. Schrodinger gave a recipe for constructing this operator from the expression of total energy of the system. The total energy of the system takes into account the kinetic energies of all the subatomic particles, attractive potential between the electrons and the nuclei, and repulsive potential among the electrons and nuclei individually. Solutions of this equation gives E and psi. Hydrogen atom and the Schrodinger equation. When Schrodinger equation is solved for hydrogen atom, the solution gives the possible energy levels the electron can occupy and the corresponding wave functions, that is psi, of the electron associated with the energy level. These quantized energy states and corresponding wave functions, which are characterized by a set of three quantum numbers, in bracket principal quantum number represented as small letter n, azimuthal quantum number represented as small letter l, and magnetic quantum number represented as ml, arises as a natural consequence in the solution of the Schrodinger equation, which an electron is in any energy state. The wave function of corresponding to that energy state contains all information about the electron. The wave function is a mathematical function whose value depends upon the coordinates of the electron in the atom and does not carry any physical meaning. Such wave functions of hydrogen or hydrogen-like species with one electron are called atomic orbitals. Such wave functions pertaining to one electron species are called one-electron systems. The probability of finding an electron at a point within an atom is proportional to the psi square at that point. The quantum mechanical results of the hydrogen atom successfully predict all aspects of the hydrogen atom spectrum, including some phenomena that could not be explained by Bohr model. Application of Schrodinger equation to multi-electron atoms presents a difficulty. The Schrodinger equation cannot be solved exactly for a multi-electron atom. This difficulty can be overcome by using approximate methods. Such calculations with the aid of modern computers showed that orbitals in atoms other than hydrogen do not differ in any radical way from the hydrogen orbitals discussed above. The principal difference lies in the consequence of increased nuclear charge. Because of this, all orbitals are somewhat contracted. Further, as you shall see later, unlike orbitals of hydrogen or hydrogen-like species whose energy depend only on the quantum number n, the energy of the orbitals in multi-electron atoms depend on the quantum numbers n and l. Important features of the quantum mechanical model of atom. Quantum mechanical model of atom is the picture of the structure of the atom, which emerges from the application of the Schrodinger equation to atoms. The following are the important features of the quantum mechanical model of atom. First one, the energy of electron in atoms is quantized. For example, when electrons are bound to the nucleus in atoms. Second one, the existence of quantized electronic energy levels is a direct result of the wave-like properties of electrons and are allowed solutions of Schrodinger wave equation. Third one, both the exact position and exact velocity of an electron in an atom cannot be determined simultaneously. The path of an electron in atom therefore can never be determined or known accurately. That is why, as you shall see later on, one talks of only probability of finding the electron at different points in an atom. Fourth one, an atomic orbitals is the wave function psi for an electron in an atom. Whenever an electron is described by a wave function, we say that the electron occupies that orbital. Since many such wave functions are possible for an electron, there are many atomic orbitals in an atom. These one electron orbital wave functions or orbitals from the basis of the electronic structure of atoms. In each orbital, the electron has a definite energy. An orbital cannot contain more than 2 electrons. In a multi-electron atom, the electrons are filled in various orbitals in the order of increasing energy. For each electron of a multi-electron atom, there shall therefore be an orbital wave function characteristic of the orbital it occupies. All the information about the electron in an atom is stored in its orbital wave function, that is represented as psi, and quantum mechanics makes it possible to extract this information out of psi. Fifth point, the probability of finding an electron at a point within an atom is proportional to the square of the orbital wave function, that is psi square, at that point. Psi square known as probability density and is always positive. Therefore, the value of psi square at different points within an atom, it is possible to predict the region around the nucleus where electron will most probably be found. 2.6.1 Orbitals and quantum numbers. A large number of orbitals are possible in an atom. Qualitatively, these orbitals can be distinguished by their size, shape, and orientation. An orbital of smaller size means there is more chance of finding electron near the nucleus. Similarly, shape and orientation mean that there are more probability of finding the electron along certain directions than along others. Atomic orbitals are precisely distinguished by what are known as quantum numbers. Each orbital is designated by 3 quantum numbers labeled as n, l, and ml. The principal quantum number n is a positive integer with value of n equal to 1, 2, 3 and so on. The principal quantum number determines the size and to large extent the energy of the orbital. For hydrogen atom and hydrogen-like species, that is helium plus, Li2 plus, etc., energy and size of the orbital depends only on n. The principal quantum numbers also identifies the shell. With the increasing in value of n, the number of allowed orbital increases and are given by n square. All the orbitals of a given value of n constitute a single shell of atom and are represented by the following letters. Shell will be represented as K, L, M, N, for n will be equal to 1, 2, 3, 4. Size of an orbital increases with increase of principal quantum number, that is n. In other words, the electron will rotate away from the nucleus. Since energy is required in shifting away the negatively charged electron from the positively charged nucleus, the energy of an orbital will increase with increase of n. Azimuthal quantum number, represented as small letter l, is also known as orbital angular momentum or subsidiary quantum number. It is defined the three-dimensional shape of the orbital for a given value of n, l can have n values ranging from 0 to n minus 1. That is, for a given value of n, the possible value of l are 0, 1, 2 and so on up to n minus 1. For example, when n equal to 1, value of l is only 0. For n equal to 2, the possible value of l can be 0 and 1. For n equal to 3, the possible l value are 0, 1 and 2. Each shell consists of one or more subshells or sublevels. The number of subshells in a principal shell is equal to value of n. For example, in the first shell, n will be equal to 1. There is only one subshell which corresponds to l equal to 0. There are two subshells l equal to 0 and 1 in the second shell, that is n equal to 2. 3 in the third shell and so on. Each subshell is assigned as azimuthal quantum number l. Subshell corresponding to different values of l are represented by the following symbols. Value of l will be 0, 1, 2, 3, 4 and so on. Notation for subshell will be S, P, D, F, G, H and so on. Table 2.4 shows the permissible values of L for a given principal quantum number and the corresponding subshell notation. Table 2.4 Subshell notations. For n equal to 1 and L equal to 0, subshell notation will be 1s. For n equal to 2, L equal to 0, subshell notation will be 2s. For n equal to 2, L equal to 1, subshell notation will be 2p. For n equal to 3, L equal to 0, subshell notation will be 3s. For n equal to 3, L equal to 1, subshell notation will be 3p, and so on. Magnetic orbital quantum number ML gives the information about the spatial orientation of the orbital with respect to standard set of coordinate axes. For any subshell defined by L value, 2L plus 1 values of ML are possible, and these values are given by ML will be equal to minus L, minus of L minus 1, minus of L minus 2, so on, 0, 1, so on, L minus 2, L minus 1, L. Thus, for L equal to 0, the only permitted value of ML will be 0. That is, 2 into L value is 0. So, 2 into 0 plus 1, that will be equal to 1. 1 s orbital is possible for L equal to 0. For L equal to 1, ML can be minus 1, 0 and plus 1. So, therefore, there are 3 p orbitals are possible. For L equal to 2, ML value will be minus 2, minus 1, 0, plus 1 and plus 2. Therefore, 5 d orbitals are possible. It should be noted that the value of ML are derived from L and that the value of L are derived from the value of N. Each orbital in an atom, therefore, is defined by a set of values of for N, L and ML. An orbital described by the quantum numbers N will be equal to 2, L will be 1, ML will be 0 is an orbital in the p subshell of the second shell. The following chart gives the relation between the subshell and the number of orbitals associated with it. Value of L will be equal to 0, 1, 2, 3 and so on. Subshell notation will be SP, DF and so on. Number of orbitals will be 1, 3, 5, 7 and so on. Electron spin is represented as S. The 3 quantum numbers labeling in atomic orbital can be used equally well to define its energy, shape and orientation. But all these quantum numbers are not enough to explain the line spectra observed in the case of multi-electron atoms, that is, some of the lines actually occurred in doublets, triplets, etc. This suggests the presence of few more energy levels than the predicted by 3 quantum numbers. In 1925, George Uhlenbeck and Samuel Goudsmit proposed the presence of 4th quantum number known as electron spin quantum number, represented as ms. An electron spin around its own axis much in a similar way as Earth spin around its own axis while revolving around the Sun. In other words, an electron has, besides the charge and mass, intrinsic spin angular quantum number, spin angular momentum of an electron. A vector quantity can have 2 orientations related to chosen axis. These 2 orientations are distinguished by the spin quantum numbers ms, which can take the values of plus half or minus half. These are called the 2 states of the electron and are normally represented by 2 arrows, spin up and spin down. 2 electrons that have different ms values are said to have opposite spins. An orbital cannot hold more than 2 electrons, and these 2 electrons should have opposite spins. To sum up, the following 4 quantum numbers provide the following information. First one, N defines the shell, determines the size of the orbital and also to a large extent the energy of the orbital. Second point, there are N subshells in the nth shell. L identifies the subshell and determines the shape of the orbital. There are 2L plus 1 orbitals of each type in a subshell, that is 1 s orbital for L value equal to 0, 3 p orbitals for L value equal to 1 and 5 d orbitals for L value equal to 2 per subshell. To some extent, L also determines the energy of the orbital in a multi-electron atom. Third point, ML designates the orientation of the orbital For a given value of L, ML has 2L plus 1 values. The same as the number of orbitals per subshell, it means that the number of orbitals is equal to the number of ways in which they are oriented. Fourth point, MS refers to orientation of the spin of the electron. 2.6.2 Shapes of atomic orbitals. The orbital wave function or Xi for an electron in an atom has no physical meaning. It is simply a mathematical function of the coordinates of the electron. However, for different orbitals, the plots of corresponding wave functions as a function of r, distance from the nucleus, are different. Gives such plots for 1s, that is n equal to 1 and L equal to 0, and 2s for n equal to 2 and L equal to 0 orbitals. According to the German physicist Max Born, the square of a wave function at a point gives the probability density of the electron at that point. The variation of Xi square as a function of r for 1s and 2s orbitals is given in figure 2.12b. Here again you may note that the curves for 1s and 2s orbitals are different. It may be noted that for a 1s orbital, the probability density is maximum at the nucleus and it decreases sharply as we move away from it. On the other hand, for 2s orbital, the probability density first decreases sharply to 0 and again starts increasing. After reaching a small maxima, it decreases again and approaches to 0 as the value of r increases further. The region where this probability density function reduces to 0 is called nodal surfaces, or simply nodes. In general, it has been found that ns orbitals has n-1 nodes. That is, number of nodes increases with the increasing of principal quantum number, that is n. In other words, number of nodes for 2s orbital is 1, 2 for 3s orbital, and so on. This probability density variation can be visualized in terms of charge cloud diagram. In these diagrams, the density of the dots in a region represents electron probability density in that region. Boundary surface diagrams of constant probability density for different orbitals give a fairly good representation of the shapes of the orbitals. In this representation, a boundary surface or contour surface is drawn in a space for an orbitals on which the value of probability density, that is Xi square, is constant. In principle, many such boundary surfaces may be possible. However, for a given orbital, only that boundary surface diagram of constant probability density is taken to be a good representation of the shape of the orbital, which encloses a region or volume in which the probability of finding the electron is very high, say 90%. The boundary surface diagram for 1s and 2s orbitals are given in figure 2.13b. One may ask a question, why do we not draw a boundary surface diagram which bounds a region in which the probability of finding the electron is 100%? The answer to this question is that the probability density Xi square has always some value. However small it may be at any finite distance from the nucleus. It is therefore not possible to draw a boundary surface diagram of a rigid size in which the probability of finding the electron is 100%. Boundary surface diagram for a s orbital is actually a sphere centered on the nucleus. In 2 dimensions, this sphere looks like a circle. It encloses a region in which probability of finding the electron is about 90%. Thus, we see that 1s and 2s orbitals are spherical in shape. In reality, all the s orbitals are spherically symmetric, that is, the probability of finding the electron at a given distance is equal in all the directions. It is also observed that the size of s orbital increases with increasing in n, that is, 4s is greater than 3s, that is greater than 2s, that is greater than 1s. And the electron is located further away from the nucleus as the principal quantum number increases. Boundary surface diagram for three 2p orbitals are shown in 2.14. In these diagrams, the nucleus is at the origin. Here, unlike s orbitals, the boundary surface diagrams are not spherical. Instead, each p orbital consists of two sections called lobes that are on either side of the plane that passes through the nucleus. The probability density function is 0 on the plane where two lobes touch each other. The size, shape, and energy of the three orbitals are identical. They differ, however, in the way the lobes are oriented. Since the lobes may be considered to lie along x, y, or z axis, they are given the designations 2px, 2py, and 2pz. It should be understood, however, that there is no simple relation between the values of ml, that is -1, 0, and +1, and the xyz directions. For our purpose, it is sufficient to remember that because there are three possible values of ml, there are therefore three p orbitals whose axes are mutually perpendicular. Like s orbital, p orbital increase in size and energy with increasing in the principal quantum number, and hence the order of energy and size of the various p orbitals is 4p is greater than 3p, 3p is greater than 2p. Further, like s orbitals, the probability density functions for p orbitals also pass through value 0. Besides at 0 and infinite distance, as the distance from the nucleus increases, the number of nodes are given by the n-2, that is the number of radial nodes is 1 for 3p orbital, 2 for 4p orbital, and so on. For L equal to 2, the orbital is known as d orbital and the minimum value of principal quantum number, that is n, has to be 3. As the value of L cannot be greater than the n-1, there are 5 ml values. For L equal to 2, thus there are 5 d orbitals. The boundary surface diagram of d orbital are shown in figure 2.15. The 5d orbital are designated as dxy, dyz, dxz, dx square minus y square, and dz square. The shapes of first 4 d orbitals are similar to each other, whereas that of fifth one, dz square, is different from others. But all 5 3d orbitals are equivalent in energy. The d orbitals for which n is greater than 3 also have shapes similar to 3d orbital, but differ in energy and size. Besides the radial nodes, the probability density function for np and nd orbitals are 0 at the place passing through the nucleus. For example, in case of pz orbital, xy plane is a nodal plane. In case of dxy orbital, there are two nodal planes passing through the origin and bisecting the xy plane containing z-axis. These are called angular nodes, and number of angular nodes are given by L, that is 1 angular node for p orbitals, 2 angular nodes for d orbitals, and so on. The total number of nodes are given by n-1, that is sum of L angular nodes and n-L-1 radial nodes. 2.6.3 Energies of orbitals. The energy of an electron in an hydrogen atom is determined solely by the principal quantum number. Thus, the energy of the orbitals in hydrogen atom increases as follows. 1s is less than 2s, that will be equal to 2p, that will be less than 3s, that will be equal to 3p, that will be further equal to 3d, which is less than 4s, which will be equal to 4p and 4d, and that will be equal to 4f, which is less than, and so on, and is depicted in figure 2.16. Although the shapes of 2s and 2p orbitals are different, an electron has the same energy when it is in the 2s orbital as when it is present in 2p orbital. The orbitals having the same energy are called degenerate. The 1s orbital in a hydrogen atom, as said to earlier, correspond to the most stable condition and is called the ground state. And an electron residing in this orbital is most strongly held by the nucleus. An electron in the 2s, 2p or higher orbitals in a hydrogen atom is in excited state. The energy of an electron in a multi-electron atom, unlike that of hydrogen atom, depends not only on its principal quantum number but also on its azimuthal quantum number. That is, for a given principal quantum number, S, P, D, F all have different energies. Within a principal quantum number, the energy of orbitals increases in the order S, which is less than P, which is less than D, and which is less than F. For higher energy levels, these differences are sufficiently pronounced and staggering of orbital energy may result. Example, 4s is less than 3d and 6s is less than 5d. 4f is less than 6p. The main reason for having different energies of the subshells is mutual repulsion among the electrons in multi-electron atoms. The only electrical interaction present in the hydrogen atom is the attraction between the negatively charged electron and the positively charged nucleus. In multi-electron atoms, besides the presence of attraction between the electron and nucleus, there are repulsion terms between every electron and other electrons present in the atom. Thus, the stability of an electron in a multi-electron atom is because total attractive interactions are more than the repulsive interactions. In general, the repulsive interaction of the electrons in the outer shell with the electrons in the inner shell are more important. On the other hand, the attractive interactions of an electron increases with increasing of positive charge on the nucleus. Due to the presence of electrons in the inner shells, the electrons in the outer shell will not experience the full positive charge of the nucleus. The effect will be lower due to the partial screening of positive charge on the nucleus by the inner shell electrons. This is known as the shielding effect or shielding of the outer shell electrons from the nucleus by the inner shell electrons. And the net positive charge experienced by the outer electrons is known as effective nuclear charge. Despite the shielding of the outer electrons from the nucleus by the inner shell electrons, the attractive force experienced by the outer shell electrons increases with increasing of nuclear charge. In other words, the energy of the interaction between the nucleus and electron decreases with the increasing of atomic number. Both the attractive and repulsive interactions depend upon the shell and shape of the orbital in which the electron is present. For example, electrons present in spherical shaped, so s orbital shields the outer electrons from the nucleus more effectively as compared to the electrons present in p orbital. Similarly, electrons present in p orbitals shield the outer electrons from the nucleus more than the electrons present in d orbital. Even though all these orbitals are present in the same shell, further within a shell, due to spherical shape of s orbital, the s orbital electron spends more time close to the nucleus in comparison to p orbital electron, which spends more time in the vicinity of the nucleus in comparison to d orbital electron. In other words, for a given shell, the Z effective experienced by the electron decreases with increasing of azimuthal quantum number. That is, the s orbital electron will be more tightly bound to the nucleus than p orbital electron, which in turn will be better tightly bound than the d orbital electron. The energy of electron in s orbital will be lowered than that of p orbital electron, which will be less energy than that of d orbital electron, and so on. Since the extent of shielding from the nucleus is different for electrons in different orbitals, it leads to the splitting of energy levels within the same shell. That is, energy of electron in an orbital, as mentioned earlier, depends on the value of n and l. Mathematically, the dependence of energies of the orbitals on n and l are quite complicated, but one simple rule is that the lower the value of n plus l for an orbital, the lower is its energy. If two orbitals have the same value of n plus l, the orbital with the lower value of n will have the lower energy. The table 2.5 illustrates the n plus l rule, and figure 2.16 depicts the energy level of multi-electron atoms. It may be noted that different subshells of a particular shell have different energies in case of multi-electron atoms. However, in hydrogen atom, these have the same energy. Lastly, it may be mentioned here that energies of orbitals in the same subshell decreases with increasing in atomic number. For example, energies of 2s orbital of hydrogen atom is greater than that of 2s orbital of lithium, and that of lithium is greater than that of sodium, and so on. That is, E2s of hydrogen atom will be greater than E2s of lithium, which will be greater than E2s of sodium, which will be further greater than E2s of potassium. 2.6.4 Filling of orbitals in atom. The filling of electrons into the orbitals of different atoms takes place according to Aufbau principle, which is based on Pauli's exclusion principle, the Hund's rule of maximum multiplicity, and the relative energies of orbitals. Aufbau principle. The word Aufbau is German, means building up. The building up of orbitals means the filling up of orbitals with the electrons. The principle states in the ground state of the atoms, the orbitals are filled in the order of their increasing energies. In other words, electrons first occupy the lowest energy orbital available to them and enter into higher energy orbitals only after the lower energy orbitals are filled. As you have learned above, energies of a given orbital depends upon effective nuclear charge, and different types of orbitals are affected to different extent. Thus, there is no single ordering of energies of orbitals which will be universally correct for all atoms. However, following order of energy of the orbitals is extremely useful. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 4f, 5d, 6p, 7s. The order may be remembered by using the method given in figure 2.17. Starting from the top, the direction of arrows gives the order of filling of orbitals. That is, starting from the right top to bottom left with respect to placement of outermost valence electrons. It is remarkably accurate for all atoms. For example, valence electron in potassium must choose between 3d and 4s orbitals, and as predicted by this sequence, it is found in 4s orbital. The above order should be assumed to be the rough guide to filling up of energy levels. In many cases, the orbitals are similar in energy, and small changes in atomic structure may bring about a change in the order of filling. Even then, the above series is a useful guide to the building up of electronic structure of an atom, provided that it is remembered that exceptions may occur. Pauli's exclusion principle. The number of electrons to be filled in various orbitals is restricted by exclusion principle given by Austrian scientist Wolfgang Pauli. According to this principle, no two electrons in an atom can have the same set of 4 quantum numbers. Pauli's exclusion principle can also stated as only 2 electrons may exist in the same orbital, and these electrons must have opposite spin. This means that the 2 electrons can have the same value of 3 quantum numbers n, l and ml, but must have the opposite spin quantum number. The restriction imposed by Pauli's exclusion principle on the number of electrons in an orbital helps in calculating the capacity of electrons to be present in any subshell. For example, subshell 1s comprises one orbital and thus has the maximum number of electrons present in 1s subshell can be 2. In P and D subshells, the maximum number of electrons can be 6 and 10 and so on. This can be summed up as the maximum number of electrons in the shell with principal quantum number n is equal to 2n square. Hund's rule of maximum multiplicity. This rule deals with the filling of electrons into the orbitals belonging to the same subshell. It states pairing of electrons in the orbitals belong to the same subshell does not take place until each orbital belonging to that subshell has got 1 electron each, that is, it is singly occupied. Since there are 3p and 5d and 7f orbitals, therefore a pairing of electrons will start in the p, d and f orbitals with the entry of 4th, 6th and 8th electron respectively. It has been observed that half-filled and fully filled degenerate set of orbitals acquire extra stability due to their symmetry. 2.6.5 Electronic configuration of atoms. The distribution of electrons into orbitals of an atom is called its electronic configuration. If one keeps in mind the basic rule which governs the filling of different atomic orbitals, the electronic configurations of different atoms can be written very easily. The electronic configuration of different atoms can be represented in two ways. For example, first one is S power A, P power B, D power C notation. Second one, orbital diagram. In the first notation, the subshell is represented by the respective letter symbol and the number of electrons present in the subshell is depicted as the superscript like ABC, etc. The similar subshell represented for different shells is differentiated by writing the principal quantum number before the respective subshell. In the second notation, each orbital of subshell is represented by a box and electron is represented by the arrow, a positive spin or a negative. The advantage of second notation over the first is that it represents all the four quantum numbers. The hydrogen atom has only one electron which goes into the orbital with the lowest energy, namely 1s. The electronic configuration of hydrogen atom is 1s1, meaning that it has one electron in 1s orbital. The second electron in helium can also occupy the 1s orbital. Its configuration is therefore 1s2. As mentioned above, the two electrons differ from each other with opposite spin, as can be seen from the orbital diagram. The third electron of lithium is not allowed in the 1s orbital because of Pauli exclusion principle. Therefore, it takes the next available choice, namely the 2s orbital. The electronic configuration of lithium is 1s2 2s1. The 2s orbital can accommodate one more electron. The configuration of beryllium atom is therefore 1s2 2s2. In the next six elements, boron, carbon, nitrogen, oxygen, fluorine, and neon, the 2p orbitals get progressively filled. This process is completed with the neon atom. The orbital picture of these elements can be represented as follows. The electronic configuration of the elements sodium to argon follow exactly the same pattern as the elements from lithium to neon, with the difference that the 3s and 3p orbitals are getting filled now. This process can be simplified if we represent the total number of electrons in the first two shells by the name of element neon. The electronic configuration of the elements from sodium to argon can be written as neon 3s1 to neon 3s2 3p6. The electrons in the completely filled shells are known as core electrons, and the electrons that are added to the electronic shells with the highest principal quantum number are called valence electrons. For example, the electrons in neon are the core electrons and the electrons from sodium to argon are the valence electrons. In potassium and calcium, the 4s orbital, being lower in energy than the 3d orbitals, is occupied by 1 and 2 electrons respectively. A new pattern is followed beginning with the scandium, the 3d orbital being lower in energy than the 4p orbital is filled first. Consequently, in the next 10 elements scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, the 5 3d orbitals are progressively occupied. We may be puzzled by the fact that chromium and copper have 5 and 10 electrons in 3d orbital rather than 4 and 9 as their position would have indicated with 2 electrons in 4s orbital. The reason is that fully filled orbitals and half-filled orbitals have extra stability. Thus, P3, P6, D5, D10, F7, F14, etc. configurations, which are either half-filled or fully filled, are more stable. Chromium and copper therefore adopt the D5 and D10 configuration. With the saturation of the 3d orbitals, the filling of the 4p orbital starts at gallium and it's complete at krypton. In the next 18 elements from rubidium to xenon, the pattern of filling the 5s, 4d and 5p orbitals are similar to that of 4s, 3d and 4p orbitals as discussed above. Then comes the turn of 6s orbital. In cesium and the barium, this orbital contains 1 and 2 electrons respectively. Then from lanthanum to mercury, the filling up of electrons takes place in 4f and 5d orbitals. After this, filling of 6p, then 7s and finally 5f and 6d orbitals takes place. The elements after uranium are all short-lived and all of them are produced artificially. The electronic configuration of known elements determined by spectroscopic methods are tabulated in table 2.6. One may ask, what is the utility of knowing the electronic configuration? The modern approach to the chemistry in fact depends on almost entirely on electronic distribution to understand and explain chemical behavior. For example, questions like why two or more atoms combine to form molecules, why some elements are metals while others are non-metals, why elements like helium and argon are not reactive but elements like the halogens are reactive. Find simple explanation from the electronic configuration. These questions have no answer in the Daltonian model of atom. A detailed understanding of the electronic structure of atom is therefore very essential for getting an insight into the various aspects of modern chemical knowledge. 2.6.6 Stability of completely filled and half-filled subshells. The ground state electronic configuration of the atom of an element always corresponds to the state of the lowest total electronic energy. The electronic configuration of most of atoms follow the basic rules given in section 2.6.5. However, in certain elements such as copper or chromium, where two subshells like 4s and 3d differ slightly in their energies, an electron shifts from a subshell of lower energy, that is 4s, to the subshell of higher energy 3d, provided such a shift results in all orbitals of the subshell of higher energy getting either completely filled or half filled. The valence electronic configuration of chromium and copper therefore are 3d5 4s1 and 3d10 4s1 respectively, and not 3d4 4s2 and 3d9 4s2. It has been found that there is extra stability associated with these electronic configurations. Causes of stability of completely filled and half-filled subshells. The completely filled and completely half-filled subshells are stable due to the following reasons. First one, symmetrical distribution of electrons. It is well known that symmetry leads to stability. The completely filled or half-filled subshells have symmetrical distribution of electrons in them and they are more stable. Electrons in the same subshell have equal energy but differ spatial distribution. Consequently, their shielding of one another is relatively small and the electrons are more strongly attracted by the nucleus. Second point, exchange energy. The stabilizing effect arises whenever two or more electrons with the same spin are present in the degenerate orbitals of a subshell. These electrons tend to exchange their position and the energy released due to this exchange is called exchange energy. The number of exchanges that can take place in maximum when the subshell is either half-filled or completely filled. As a result, the exchange energy is maximum and so is the stability. You may note that the exchange energy is at the basis of Hund's rule that electrons which enter orbitals of equal energy have parallel spins as far as possible. In other words, the extra stability of half-filled and completely filled subshells is due to relatively small shielding, smaller Coulombic repulsion energy, and larger exchange energy. Details about the exchange energy will be dealt with higher classes. Summary. Atoms are the building blocks of elements. They are smallest parts of an element that chemically react. The first atomic theory, proposed by John Dalton in 1808, regarded atom as the ultimate indivisible particle of matter. Towards the end of 19th century, it was proved experimentally that atoms are divisible and consist of three fundamental particles: electrons, protons, and neutrons. The discovery of subatomic particles led to the proposal of various atomic models to explain the structure of atom. Thomson in 1898 proposed that an atom consists of uniform sphere of positive electricity with electrons embedded into it. This model, in which mass of the atom is considered to be evenly spread over the atom, was proved wrong by Rutherford-Framer's alpha particle scattering experiment in 1909. Rutherford concluded that atom is made up of tiny positively charged nucleus at its center with electrons revolving around it in circular orbits. Rutherford model, which resembles the solar system, was no doubt an improvement over Thomson's model, but it could not account for the stability of atom, that is, why electron does not fall into the nucleus. Further, it was also silent about the electronic structure of atoms, that is, about the distribution and relative energies of electrons around the nucleus. The difficulties of the Rutherford model were overcome by Niels Bohr in 1913 in his model of the hydrogen atom. Bohr postulated that electrons move around the nucleus in circular orbits. Only certain orbits can exist, and each orbit corresponds to a specific energy. Bohr calculated the energy of electron in various orbits and for each orbit predicted the distance between the electron and nucleus. Bohr model, though offering a satisfactory model or explaining the spectra of hydrogen atom, could not explain the spectra of multi-electron atom. The reason for this was soon discovered. In Bohr model, an electron is regarded as the charged particle moving in well-defined circular orbit about the nucleus. The wave character of an electron is ignored in Bohr's theory. An orbit is a clearly defined path, and this path can completely be defined only if both exact position and exact velocity of the electron at the same time are known. This is not possible according to Heisenberg uncertainty principle. Bohr model of the hydrogen atom therefore not only ignores the dual behavior of electron but also contradicts Heisenberg uncertainty principle. Erwin Schrödinger in 1926 proposed an equation called Schrödinger equation to describe the electron distribution in space and the allowed energy levels in atoms. This equation incorporates de Broglie's concept of wave-particle duality and is consistent with the Heisenberg uncertainty principle. When Schrödinger equation is solved for an electron in the hydrogen atom, the solution gives the possible energy states the electron can occupy. These quantized energy states and corresponding wave functions, which are characterized by a set of three quantum numbers, that is principal quantum number, azimuthal quantum number, and magnetic quantum number, arises as a natural consequence in the solution of the Schrödinger equation. The restriction on the values of these three quantum numbers also come naturally from this solution. The quantum mechanical model of the hydrogen atom successfully predicts all aspects of the hydrogen atom spectrum, including some phenomena that could not be explained by the Bohr model. According to the quantum mechanical model of atom, the electron distribution of an atom containing a number of electrons is divided into shells. The shells in turn are thought to consist of one or more subshells, and subshells are consumed to be composed of one or more orbitals, which the electrons occupy. While for hydrogen and hydrogen-like systems, all the orbitals within a given shell have same energy. The energy of the orbitals in the multi-electron atom depends upon the value of n and l. The lower the value of n plus l for an orbital, the lower is its energy. If two orbitals have the same n plus l value, the orbital with the lower value of n has the lower energy. In an atom, many such orbitals are possible, and electrons are filled in these orbitals in order of increasing energy. Accordance with the Pauli's exclusion principle, that is, no two electrons in an atom can have the same set of 4 quantum numbers, and Hund's rule of maximum multiplicity, that is, pairing of electrons in the orbitals belonging to the same subshell does not take place until each orbital belonging to the subshell has got 1 electron each, that is singly occupied. This forms the basis of electronic structure of atoms. We have just completed second chapter reading. Stay connected, keep learning. Thank you for watching.